Thank you for coming. I thought maybe, if I put Linux in the title, then some people would get scared, but I'm very proud of you that you did not. And so welcome to this talk on how containers work. I mean, it is going to be a talk about Linux containers because I personally don't really believe Windows containers are super hot and relevant yet. But a lot of the principles we will talk about, a lot of the mechanisms are similar on Windows. They're not, of course, the same because it's a different kernel after all. But a lot of the concepts and the ideas anyway, they should be fairly similar on Windows. So thanks for coming. My name is Sasha. I see a lot of familiar faces. This is my 5th, 6th, I don't remember which .next it is, but I'm very happy to be here as always. And so let's get started. Why did I even propose this talk for a .NET development conference? Where is this coming from? So basically, I checked Stack Overflow. And so people are asking various good questions. People are asking, how is Docker different from a normal virtual machine? What am I supposed to get out of this whole new thing that I'm supposed to learn, operate, and understand? How do I get memory usage of processes running in a container? And how do I explain what I'm seeing? Like, why is this high and this low? Why is the killer, the out-of-memory killer, killing my application? This is specifically for Java, but the same thing will happen to your .NET processes as well. So why is this happening? How can I limit certain aspects of my container's processes, like the I/O that this container is allowed to consume, the number of disks, reads, or writes? Why can't I saturate my CPUs? What could possibly be stopping my container from using all the available resources? How come certain things don't work when I try to do them from inside a container and I get errors like operation not permitted, operation not permitted? And why are Docker images so large? Why do I take this tiny thing and add an editor and Git and my image is 500 megabytes bigger? Where is this coming from? And why, if you check in the container, the image size is not the same as the size of all the directories and files inside the actual container? So how to explain this discrepancy? So these are some of the questions which led me to build this talk, because I think .NET developers are and will operate containers on Linux, and you need to be able to answer these questions if you think you are going to successfully work with Linux containers. And so my examples will use .NET Core, and I'll show you at the end how to build smaller .NET Core images. So there will be some specifics, some .NET specifics in this talk, but generally you can apply it to your Java applications, Node.js, C++, whatever you want to run in a container. I think these things matter. So we'll talk about why containers very briefly, because I think you've had enough Docker introduction talks at this point. And then we'll talk about the building blocks that containers use on Linux. And these are security profiles, namespaces, control groups, overlay file systems, and we'll talk about building container images which are as small as possible. So as a very quick introduction or refreshment, if you've not seen containers yet, hardware virtualization is on the left, and that's what we used to do in the past. We would basically have a whole computer inside a virtual machine, and that computer contains the operating system kernel, the user space files and libraries you need for that operating system, and also your application libraries and executables. With containers, or OS virtualization, shown on the right, we do not copy the kernel and everything necessarily for the specific application. We can share a lot more stuff between containers, and we'll talk about the mechanisms which make it possible. And as a result, we get much smaller images. We get much smaller things that we then call container images compared to a full-blown virtual machine image. And the difference can be 2 or 3 orders of magnitude, so there is something to be gained here. And there's a lot of potential for sharing. If you use a lot of .NET stuff, you probably have multiple containers running various .NET services. And you can share the file systems for the Linux distribution, the Linux kernel, of course, libraries, the .NET framework itself, between all the different .NET containers you will have. By the way, maybe someone wants to do like a count of how many times I'm going to say container, and then at the end, maybe you get like 1 cent for each time, and that's going to be quite a lot of money, I'm afraid. So that's, again, just to refresh your mind why we need this thing. And some of the reasons people are using containers include simplifying configuration, because it's very easy to build containers from a nice textual definition of what goes inside and how to build the whole thing. You get a consistent environment that you can ship from development to testing to production to staging and so on. You get a much smaller deployment footprint. Again, I'm going over this quickly because I assume you've heard a Docker talk and you've been sold on why this is a good thing, and you want to understand how it works and how to really operate it correctly. So these are the building blocks for Linux containers. On this diagram, you see the Linux kernel on the bottom, and then on top of the kernel, you see 3 containers. One is running Node.js, the other is running ASP.NET Core, and the third one is running some kind of Java application, God forbid. And so here are the 4 things we'll talk about in this talk. The first is various restrictions or quotas that you can place on each container. For example, the Java process, it only needs 2 gigabytes of RAM, but the .NET application, it needs 4 gigabytes, and it also needs 2 CPUs. But OK, I don't want to let it use any more than that. So the mechanism in the Linux kernel, which helps you set those limits, is called control groups. And we'll talk about control groups in a little while. The second thing you want to prevent containers from doing is nasty stuff to the host machine. For example, there is a system called reboot, which will reboot your host. So you don't want your containers to be able to do that, to reboot the host machine, and a lot of other stuff. So you want to restrict what containers can do by using security profiles. And we'll talk about those and capabilities as well. The third thing you want to sort of restrict or prevent, isolate containers from each other so they can't see each other, they can't interfere with each other. Like maybe kill a process which belongs to another container. Sounds like a bad idea. So that is something we can prevent using namespaces, which is a kernel mechanism that isolates containers from each other. And finally, the files you put inside the container, you want to share them as much as possible. So if you have multiple containers sharing the same files, you don't want to duplicate them on disk. You want to reuse as much as possible. And that is made possible by copy-on-write overlaid file systems. So these are the 4 things we'll talk about. And really, there is no such thing. It's kind of funny. There is no such thing in the Linux kernel as a container. There is nothing in the kernel that tracks what a container is, except for these various things. And so really, the ingenuity of Docker Inc. and other runtimes is taking all these building blocks together and marketing them really, really nicely. And if you look at the fundamental ideas, they've been available for other operating systems like Solaris, for example, a lot earlier, a lot before Docker came about. And they sort of got their inspiration from there. So let's start with security profiles, just to get this out of the way. Docker uses 2 different mechanisms to restrict what containers can do. The first is called kernel security modules. And that includes stuff like AppArmor, for example, which we're not going to look at more closely today. But it is a text-based configuration language, which the kernel then uses to restrict what a containerized process can do. Actually, what any process that profile is applied to can do. And that can be things like you can't write specific files, or you can't use specific system calls, or you can't use sockets to do this and that. So Docker uses that, and it has a default AppArmor profile, if you use AppArmor, that will restrict what your container can do. But that's not always used. AppArmor is optional, and Docker can live without it. The one thing that Docker typically uses on all deployments is seccomp. And that is a Linux kernel concept, which has been around for a while, and it lets you restrict the system calls that a process can perform. So if you apply a seccomp profile to a process, you can do things like prevent reboot, so the process can't reboot the host machine, or change the operating system time, or unmount important devices, or use sockets if you don't like them. So you can restrict what a container can do. And there is a good default. Docker has a default seccomp profile, which sounds like a good idea. And maybe you've been using containers for 2 years and never heard of seccomp before. But sometimes things break, and this is where you need to know what seccomp is. So let's do a quick experiment. Suppose you run this Docker container using one of the Microsoft official images, and you put your app inside. So this is running. And then you use docker exec, which we'll talk about a little later, to get a shell inside that container. This is, by the way, all these examples on the slides titled experiments, they are designed to be something that you can run as well. So if after the talk you want to do these experiments, you should be able to with just a little setup beforehand. So you got a shell, and then suppose you want to do profiling. You want to profile your .NET application in the container. So you go ahead and install perf. And I talked about .NET Core profiling at the last .next. I think the talk was published at this point. So if you want to check out how to profile .NET processes using perf, you can go ahead and do that. So in the container, we are now installing perf. And that surprisingly works, but then you can't actually run it. If you run perf, it complains, failed unexpectedly, you may not have permission to collect system-wide stats, consider tweaking perf event paranoid. So perf seems to not be able to do something, and it's even suggesting what you should do to fix the problem. Now this is a host switch that you need to toggle, and so okay, I go back to the host, and I fix the problem, I set that control to what it needs to be, that knob to what it needs to be, and I retry, and perf says the same thing. Perf event paranoid, consider tweaking, and so on. But this is just a misleading error message. Perf doesn't really have a problem with my perf event paranoid settings. What it does have a problem with is this system call it's trying to use, perf event open, which is simply blocked by Docker. It is blocked by the Docker seccomp profile. And now if you go on Stack Overflow and you start looking it up, people will tell you, well, run your container as privileged, -- privileged. And that solves all the problems in the world. But now your container processes are running as root on the host. And I'm not sure you want that as a default. And no restrictions are applied to these processes anymore. And if you do apply restrictions to these processes, they have the permissions to remove the restrictions. So you probably don't want -- privileged. The other option is add the specific syscall that is blocked to the security profile that Docker will use. And Docker takes a JSON file, which specifies the security configuration for seccomp. And so the only thing I did is just download Docker's profile and added one system call to the whitelist, to the list of allowed system calls. And then I do this. I tell Docker to use that security profile, to use that seccomp profile, and then perf just works. So just to shorten things up, this one big command installs perf and then runs it, and it works. So this is an example of using a custom security profile, and you might have to do that sort of thing in other scenarios as well, to run debugging tools, to run profiling tools, to run various diagnostics which require a specific thing that Docker blocks by default, but you don't want to run as privileged just to enable that one thing. There's also another aspect of this, which is kind of related, not to seccomp, but it's a concept called capabilities. Like 30 years ago, the permission model was quite simple, and root can basically do everything, and other standard users really can't do anything. But today, Linux has a quite fine-grained capabilities model, where processes, in order to be able to do something, require a specific capability which can be assigned or removed. And so Docker, again, removes, by default, a lot of capabilities from your process because it thinks it doesn't need them. And that includes things like capsys time, which is used to set the system time, or capsys ptrace, which I will mention in a few moments. So you can add these capabilities back. Again, you don't need privileged to get these capabilities back. Docker has a switch called cap-add, which you can use to just enable the capabilities you require. And your security people will be a lot happier. Now, Docker is also smart, and it enables certain system calls where the appropriate capability is also added. So just as an example, they usually go together. Reboot, the system call, often goes together with the sysboot capability, which is required to use that system call. So if you just add the capability, but you don't modify the seccomp profile, it would not work. But Docker takes care of that. So if you use the capability, you also get the syscall enabled. Summary so far. Don't use -- privileged. It is just basically equivalent to running as root on the host, and people do not like that, especially security people, they don't like that. And if you're interested in more details, I put some links on the slides on capabilities and seccomp as well. Let's move on to the second mechanism that isolates containers from each other, and that's namespaces. And this is slightly more exciting because all this security stuff, I mean, it's not extremely exciting. So namespaces are more interesting. Namespaces restrict the visibility of a process into other things running on the system. And there's multiple kinds of namespaces Linux has. And so if a process is inside a namespace, it only shares things with other processes in that namespace. That's generally the idea you should remember. So some examples. We have the PID namespace, the process ID namespace. And so if you put a process in a PID namespace, it gets fresh new process IDs. So the same process ID can appear multiple times on the system in different namespaces. And that's important for some reasons we'll see later. The mount namespace means that a container gets its own mount points. So basically its own view of the file system, so that you can isolate what the container can see on the file system. Extremely important to put containers apart. The net namespace helps assign a container its own network interfaces. So if you have a container that doesn't need networking, wonderful. It doesn't need to see the host's network interfaces. So you can use namespaces for that. There's a bunch of stuff you can do with namespaces. And here's a sort of basic architecture diagram of how Docker arranges these things. So you go and type into your shell, Docker run this and that. This is the Docker client, the Docker command line tool. The Docker client talks to Dockerd, which is a background service, Docker daemon. That, in turn, talks to Docker containerd, which is one of the runtimes that Docker can use, and that's the default one, containerd. And containerd then creates another process for each container you run called Docker containerd shim. And that process finally launches your container. And by launches your container, I mean it runs the initial process for your container, which might end up creating some additional processes. So there's multiple steps here. And what I want to demonstrate is where the different namespace-related stuff is taking place and what the isolation looks like, and then how to overcome the isolation, because often you want to do things from inside the container, like I did with Docker exec, and it's not really clear how you can if there are so many restrictions involved. So let's do an experiment again. Let's find the process ID for containerd. Containerd, reminder, is this guy. We have one of those. And it creates these ones. All right. So let's find its process ID. And then let's use strace with the process ID of containerd and trace only one system call called unshare. Unshare is the system call that creates new namespaces. It's a weird name, but if you think about it, it kind of makes sense. When you create a new namespace, you unshare your namespace from that new namespace. So maybe unshare makes sense. I don't know. Anyway, so you run strace, and then in a different shell, you run docker run to create, a new container with this or that image and so on. And then strace happily reports, yes, unshare was called. And the following new namespaces were created. New UTS, new IPC, new net, new PID. Not sure about new NS, need to check. I think it's just the basic flag for the rest of them. But we created multiple new namespaces in this single unshare call. And so this is where the actual isolation happens. So again, if I go back to the previous diagram for a moment, containerd uses unshare to run this containerd shim in a separate namespace, and then all the children created by the containerd shim will also run in those separate namespaces. Cool. So how does it look in practice? I mean, besides the system calls. So suppose you run two containers with the same application, doesn't really matter, and then you get a shell in both containers, and you ask which processes are running. Now, there's a reason I'm not using ps, which is the Linux command for listing processes. I'll show you later why. But instead, I just go to the proc file system, and I list the first two entries. So these are the process IDs, process ID 1 and process ID 14. These are the process IDs for the first container. OK, now let's see what the second container thinks. The second container thinks we have process IDs 1 and 25. I don't mind the 14 and the 25, but process ID 1 did appear twice already, and there's also process ID 1 on the host machine. So clearly, we're seeing the same numbers. And the only reason this is possible is because of namespaces. And by the way, from the host's perspective, if you look for these processes on the host, their process IDs are something completely different, 316 and 32,709. So in the host's PID namespace, they have different process IDs than in the container's PID namespace. And that's a good thing, because now, if this bad guy, container 2, tries to kill process ID 14, which belongs to container number 1, it's just going to fail and say there is no such process. So, good stuff. Let's see how it works for other resources, files, for example. So you go to container 1, and you create a new file. /temp file 1. And then you go to container 2 and you ls/temp. And you do find some interesting files, but not file 1. So the file system, the /temp that these two containers are seeing, are also isolated from each other. And we could do the same experiment with other namespaces as well. For example, the user namespace lets you have user IDs that are the same in two containers mapped to actually different user IDs on the host. Or the UTS namespace lets you assign the same host name to two containers, which are really not really separate hosts, but they think they are. So this is how things work. Now, there's a bunch of tools that I just want to mention. They're not super critical. There's a bunch of Linux tools that you can use to list namespaces. The first basic thing you can do is just go to /proc for your process ID and look in the NS directory. And there's a file in there for each namespace that your container is assigned to. And the files will always be there. The question is it just the default host namespace, or are these the container-specific namespaces? And the way you know is by looking at the inode number. And so that is not super friendly. And specifically, it doesn't tell you which processes are sharing a namespace, who created that namespace. You don't really know the whole hierarchy. So we have a dedicated tool called LSNS. Sort of makes sense. And here I said lsns-t PID. So print all the PID namespaces on the system. We got 3 of them. The first one is the default one, and that's it's running systemd, which is the new init process for a few years, and it's running PID1 on the host. And there's 92 processes inside. So this is the default host namespace. And then we have these two guys, these two namespaces. They only have one process in each, and they run my app, simple app. So LSNS can print which namespaces we have, and then you can use LSNS to see, for a specific process, which namespaces it belongs to. So in this example, you can see that process ID 316 belongs to a mount namespace, a UTS namespace, an IPC namespace, blah, blah, blah. And ls prints them out for you. Great, so we have the theory of namespaces, and we have isolation, which we love, but how about when you don't want isolation? How do you overcome it? What if you want to enter a container and do some stuff from inside? All right, so the basic way to do it is using nsenter, which is a very, very thin wrapper on top of a Linux system call that we'll see in a moment. nsenter has nothing to do with Docker. It will work with any namespaced process. And what it does is it enters the namespaces of that process and then runs a command for you from the namespace. There's some details with forking and having the child unshare itself. There's some stuff to be done here, but generally, nsenter will enter a namespace and then run a command. And you can tell nsenter which namespaces. So for example, -m here stands for mount. You can say which namespaces to enter and which to share with the host. Now, what is nsenter doing? Again, just as an experiment, you can see that it's using the setNS system call. So, unshare to break yourself into a new namespace, setNS to enter a new namespace. Now, setNS here is called multiple times because nsenter enters multiple namespaces in this example. I used the -a switch, which means all namespaces. So it went ahead and added itself to each of the namespaces this container, this process, is assigned. Okay, so nsenter is not typically what you use to enter a Docker container because you have docker exec. And the picture is exactly the same. When you use docker exec with an existing container to run a command inside an existing container, what containerd basically does is setNS for you. I know it's not a very big surprise, but nsenter and docker exec are more or less identical. And so all that's happening is that a new process is created and it is assigned the same namespaces as existing processes on the system. So stop thinking of containers as this magic thing which you need to enter using some special tunnels or whatnot. It's just a system call. You create a process and then you run a system call which assigns it to the same namespace. However, and this is important for the next example, the rest of the mechanisms are not now somehow applied to that process. So for example, if you just use setNS, the security constraints, the resource constraints that we'll talk about in a moment, they are not suddenly assigned to the new process. And this is where there's a difference between using docker exec and using nsenter. nsenter only enters the namespace, and docker exec takes care of other container aspects as well. And again, we'll touch on that in a moment. Okay, so what I'm going to do now is slightly more interesting. First, just as a setup, here's what I did. I created a new .NET Core console app using the Microsoft official .NET SDK image. Then I edited the new app in my terminal. Then I ran the .NET SDK container again. Whew, my clicker went crazy. I ran it again and told it to do restore NuGet packages and publish the application in release mode. And then finally, I ran yet another container, which is actually running my application. So that's just the setup. We'll use that same setup later. So just keep this in mind. Here's what I did. Great, so I have that. And the application is running in production, and everyone's like very, very happy. But then you need to do some very basic diagnostics. For example, you want to list all the processes running in that application container. So you use docker exec, which you just learned about, and you say docker exec, this is the name of my container app, and this is the command I want to run, ps. OCI runtime exec failed, container linux.go, line 296. This basically says there is no ps. The container doesn't know what you're talking about. There is no ps command in the container. And that sort of makes sense because it's a production image. It's designed for running production apps. Why the ps command would be included? Okay, so ps is not included, but ls is included. So let's go ahead and just look at /proc like we did before. Here are the processes, 1 and 15. OK, so I keep experimenting, and I discovered that process 15 is the one giving me trouble. And I need to troubleshoot it. Maybe attach a debugger, maybe use a tracing tool or something. Specifically, I want to use strace, but it's just an example. Same thing would happen if I used the GDB or LLDB, debugging tools or profiling tools. Probably the performance tool or the profiling tool also does not exist in the production container. So now what? In the beginning of the talk, I went ahead and installed it inside. I started running stuff to install the debugging tool in the container and then use it. OK, let's do it. Let's get in the container and install strace or GDB or perf or whatever it is. And then run strace. And then strace complains, operation not permitted. And here, if you go back to the beginning of the talk, I said, oh, well, let's run this container and add something to the security profile so I can use this specific tool. But here it's a lot more dangerous, because ptrace is basically a debugging API. It is used to attach like a debugger to another process. It's not something I would like my container to be able to do by default. So I'm in a pickle. I can't really afford to let my container have that privilege, but I need to use a debugging tool which requires that privilege. So I can't use containers anymore? You can. And here's how. Docker run, not Docker exec, creates a new container. But nobody said that the new container cannot share some namespaces with existing containers. Because remember, namespaces are just a system call away. So what you can do is launch a new container and tell it to share the PID namespace, for example, with the app container. So it's going to be a separate container from all other aspects, but it will run in the same PID namespace. And this new container will have the ptrace privilege, the ptrace capability assigned. So I'm not contaminating my existing container. I'm not giving it any extra privileges. I'm running a new diagnostic container which has the extra privileges I need, and I share some stuff with the original. And then inside, I can now install strace and use it successfully. And again, the same would apply to GDB or other diagnostic tools which require some extra security privileges. So this is, again, where understanding namespaces helps. It is not a magic box. It's just a system call away. You decide what to share and not to share. Just as a conclusion example for this section, Kubernetes, for example, has this concept of a pod. And in a pod, you might have multiple containers, but they share namespaces with each other. And so, for example, if you run a diagnostic container in the same pod as your application container, it will have that sort of access to processes and other things from your application containers as well. OK, cool. So that was namespaces. Let's keep going. The third thing that makes containers what they are is control groups. And this is also quite exciting, because it means you can restrict the resources that a process can use. And it's just not really something you can easily do without containers. Like, think about all the times you had a .NET application run crazy with memory usage or CPU utilization, and you just wish you had a way to really restrict the resources assigned to it. In the past, you would have to use virtual machines for that. But C groups, control groups, make it possible. So we have several kinds of C groups used by Docker and other container runtimes. The CPU C group can restrict CPU resources, memory for memory, block I/O for disk devices, and so on. And this is really nice, and it's all controlled by files in the file system. So to put restrictions on a process, you write a bunch of stuff to a file. Interesting. So let's see how it actually looks like. I'm running here the stress container image, which is just the tool that creates a bunch of threads and burns 100% CPU. And I tell it to burn 4 threads. It creates 4 threads. But then I tell Docker, only give this container half a CPU. So let's see what happens then. If you look in top, on the host or in the container, doesn't matter, you'll see that you have multiple stress threads, processes, doesn't matter. But together, they really only get 50% CPU. And each of those would like to use 100%, but they can't. So it really works. How does it work? And how do you identify this condition where you have a thread that wants more CPU, but the bad Docker is restricting its CPU usage? So here's how you identify this. One way is to look at your poor process. It has a status file in the file system, and that status file has a field called non-voluntary CTXT switches. So non-voluntary context switches is when they put handcuffs on you and push you off the stage because it's not that you wanted to go away, it's the kernel. They wanted to push you out of the CPU and replace you with someone else. Now, this can happen for non-container related reasons. So this is just the first sign, but it does say that we have lots of these non-voluntary context switches going on, except for the last process, which just creates the others and sits there. So it's not really doing anything. The more container-specific way is just looking at the cgroup files. So the default place for cgroup files is sysfs cgroup. You can mount it wherever you want. And then if you find your containers directory in there, you'll find a bunch of interesting things. For example, this is how the half CPU was specified. So there's something called CFS period microseconds, and that's set to 100,000. And there's another thing called quota microseconds, which is set to 50,000. And that basically says any processes assigned to this C group can only use 50 milliseconds out of every 100 millisecond period. And once you run out of those 50 milliseconds, you have to wait for 50 milliseconds, which is debatably good. It's good because you can restrict the resources assigned to a process, but then think about it. If you now have exceeded your quota, you will be throttled for 50 milliseconds and you will not get CPU at all. So it's probably not great for some certain kinds of applications. But anyway, that's how it works. Another way to see if it's actually happening for your process is to look at the statistics file for the C group. And that tells you that out of 8,354 periods, 8,352 times I was throttled. So I am badly, badly throttled here. Let's see the same thing for memory, because memory is quite painful for .NET applications, any garbage collected runtime. So let's see how it works for memory. Run a Docker container with a 128 megabyte memory limit. Surprisingly, this is actually enough for a hello world .NET application. But we'll see other things that are not enough. So anyway, you run your app, and then where is this limit specified? In a file. Another file called memory limit in bytes. And you see it's set to 128 megabytes, right? And what is really this memory limit, right? I could do this talk on Windows as well and ask you what is memory usage. And I can ask the same question on Linux, or there's like 35 different answers to what is really memory usage. And more than that, Linux has this feature, which is usually enabled by default, where you can actually commit more memory than you have on the machine, plus the page file. So you might have a 1 gigabyte RAM on your machine and 1 gigabyte swap, and you can still commit 10 gigabytes. It's just when you start using them that you get into trouble. And that's how Linux is by default. So there's a bunch of different ways to look at how much memory your process is really using. And again, it could be the subject of a completely different talk. Just to show you some numbers, if you look at the status file, which is what TOP and other tools use, you see there's a bunch of numbers. Virtual memory, RSS, stack, exe, PTE, shmem, file. And if you look at the C group memory statistics, there's also a bunch of numbers. Now, the C group ones are what matters, because that is what the kernel uses to decide where it's going to get rid of your process. And when that happens, when you exceed the C group memory limit, this is what it will look like if your app would even notice, but probably the kernel would just get rid of your process and put this beautiful message in the kernel message log, which says, simple app, that's my application, invoked the killer. Here was the stack trace, which you don't really care about, and it tells you it was a process in this Docker C group, which was killed as a result of a limit in that C group, and it used this much memory, and it had that limit, and it was exceeded, and you ran out of memory, and there's a bunch of additional text in there. But what will probably not happen is a nice log message on your console or an out-of-memory exception thrown and wrapped by the .NET runtime. Probably your .NET process will just keep running, and then boom, the kernel comes and takes it away. And so all these C-group memory limits are extremely aggressive and difficult for runtimes to identify. Because, again, the .NET application might be committing more memory than is available to it and running very well for 2 hours, but then when it touches one page beyond the quota, which it already allocated 2 hours ago, then the limit will be enforced and you will crash. So this is just something to be aware of. And any attempts to detect this automatically from your code will probably fail. The best thing you can do in these situations is just to restart your container automatically, at least in the current state-of-the-art condition. Final example for C groups has to do with disk I/O. This is super boring, but just so you know, because there was a question on Stack Overflow. So the block I/O C group can restrict your disk device access. And so here we run a container and we say this container can only write 10 kilobytes per second to this disk device. And then it can try whatever it wants, but it will not be able to write more than 10 kilobytes per second sustained. We have the same limits for reads as well. And you don't have to restrict bytes per second. You can also restrict operations per second. And the idea is to share all the layers that you can. So for example, you have a Debian Linux base image. And that is maybe 80 megabytes of various user space files and libraries that Debian needs. And that can be shared across all containers using Debian as the base. So it's not going to be duplicated on disk for each container if you have multiple containers using Debian. And then maybe you also use .NET Core. So you have the .NET Core base image, which is based on Debian. So all the Debian parts are not duplicated. But then you add on top the .NET runtime, garbage collector, JIT compiler, libraries, and so on. And that, again, will be shared across all the .NET application containers you will create. And even if you have an app-specific container image, like this one here, with my app DLL, that image can also be shared, that layer can also be shared if you create multiple containers running the same application. So again, share as much as possible and duplicate only the thinnest parts which are actually modified at runtime. And some people actually run containers with a read-only file system, so that nothing can even be modified at all. So the footprint of a new container on disk is exactly 0 bytes, because it's not allowed to write any new files anyway. But that's, I mean, you don't have to subscribe to that philosophy. It is still useful without it. So Docker history is the command that shows you all these layers and how big they are, how expensive they are. So this is, for example, the .NET Nightly 2.1 runtime image from Microsoft. And it has the biggest layer here is the one that actually pulls the .NET installation and extracts it to user bin.net. And that's 74 megabytes. The previous layer installs a bunch of native dependencies, and that's 7 megabytes. And the base here, the first layer here, installs another bunch of dependencies, and that is 43 megabytes. So that gives you an idea of how an image was built and what the different layers weigh, so you know what you can share and what you can't. Cool. So how do you make small images? There's a bunch of small tips here, but they're not .NET specific. We don't have a lot of time, so I'd rather skip ahead and talk about .NET images and how we can build small images. So what do you think is the hello world image size for Docker? Is it, let's say, OK, I'll ask it like this. Is it gigabytes? Raise your hand if you think it's multiple gigabytes. OK. Megabytes. All right. Hundreds of kilobytes. Tens of kilobytes. Just a few kilobytes. It's 1.85 kilobytes, which is nice, but this is a sidebar. How small can you go? Like, can you make something that actually runs and is smaller than that? So I was curious. So first of all, there is a container image called Scratch, which is 0 bytes, which is what you use when you start building an image from scratch. But you can't run it, so that's cheating. But the smallest Linux executable that you can create, and it's an actually quite interesting blog post I linked here, is 45 bytes. So you can create a container image which only has that small Linux executable inside, and it will run, and it will successfully complete, and it's a 45-byte image. Great. So I mean, containers are really awesome. You can ship 45 bytes from side to side, and it runs your whole .NET application. Not quite. So the .NET SDK image is 1.72 gigabytes, which is unfortunate. Then we have the runtime image and the runtime depths. What are these images, and why are they so different in size? So the SDK image is the one you use for building. It has compilers and NuGet and a bunch of stuff inside that you need for building applications, which is why it's big. Then you have the runtime images, and these are used for running an app. And so there's the .NET tool in there, the GC, the JIT, libraries like System Console or whatever. And that, as you can see, is 10 times smaller. So if you don't need to build an application in a container, don't use the SDK image for that container. And finally, the runtime depths images are designed for self-contained applications. And that's actually a pretty cool thing. I wish we had more time to talk about it. It's a different talk altogether. But the idea with a self-contained image is that you can produce a single directory which has your application, the .NET runtime, and the .NET class libraries all in a single directory. And then you don't need to install .NET on that machine anymore. And so there's a trade-off here, because the base image, as you can see, is 99 megabytes, which is twice as small. But then you have to add, whatever you compiled. And so when I tried it out, hello world with self-contained for Debian is 72 megabytes. So if you add 72 and 99, it's not a lot smaller than the runtime image. But we'll come back to that in a couple of moments. So what's the logical conclusion from this? If you're building an app and then packaging it in a container, don't use the same image for both stages. And Docker has, for more than a year now, this cool feature called multi-stage builds, where you build, for example, in this case, using the SDK image, produce some stuff, and then the final packaged image uses a different base and copies files from the first stage. And so as a result, you build with the big container, but you package into a smaller container. So that's clearly something you want to do. But this is still pretty big, right? I was saying it's hundreds of megabytes, maybe 200, but still quite big. So you can go even less, even smaller. Alpine is a Linux distribution which is designed, well, for very low memory environments, and containers is a good fit. It has a lot of optimizations for size, and so the Alpine base image is 4 megabytes. And it's a Linux distribution almost like any other, which is amazing. Then you have the Microsoft Alpine images, and they are unfortunately a bit bigger, but again, smaller than the Debian ones. And they are fully functional. They can run .NET apps more or less completely with all the features. And you see the runtime depths image is just 13 megabytes. That's incredible. And that's enough to run a self-contained .NET application. Of course, you need to add the application. So how much does that increase the size? So here's what I did. I built a self-contained Alpine image, and then I packaged it into this runtime depths Alpine container. And the result was 54 megabytes. And this is, I think, currently as low as you can go. And I think it's amazing, actually. And Alpine, building for Alpine is quite new. It's only now been released in .NET 2.1. And all of these Alpine-based .NET Core images are new. So this is exciting stuff. And 54 megabytes, that is comparable with other people. For example, Java or Node, you know? So the Node Alpine base image is 23 megabytes. So good for them, but then you run npm install, and it's 2 gigabytes. So that's not really a fair point to make. So you can build really, really tiny .NET Core containers with Alpine or not, if you understand which container images to use, and if you try the self-contained and then the runtime dependencies workflow. One final thing to think about before we wrap up. This is the .NET Framework 4.7 Windows image. It's actually gotten a little smaller since then, but this is an issue from GitHub that complains it's 12 gigabytes in size. So we now have 4 orders of magnitude in size between the .NET Framework Windows Server image and the Alpine self-contained image, which was 54 megabytes. And that's, I mean, it's a journey that took only 3 or 4 years, and that's really very, very surprising and exciting. So I want to wrap up with some conclusions and takeaways, and then you'll be able to follow me to the discussion zone if you have any questions. Why containers? Again, you've been to Docker talks, I hope, and so you know containers produce rapid, lightweight deployments which you can easily move from one place to another, but they still have security quota, security isolation, resource usage quotas, various kinds of visibility restrictions. So it's almost like a VM, but at a much, much lower cost. We talked about the building blocks for containers, which are security profiles, namespaces, control groups, and these layered file systems. Specifically, just to remind you what we did, security profiles are used by container runtimes to restrict which system calls or capabilities the container is allowed to use. And you can add just those. Do not use -- privilege to just add everything and run as root if you don't have to. Namespaces isolate containers from each other, but you can enter an existing container's namespace, and also you can share namespaces between containers, which is really useful for diagnostic containers. Control groups apply resource quotas to containers, and you will get killed or throttled very aggressively by the kernel if your quotas are breached. And finally, you can build really, really small .NET containers if you use the appropriate base images, if you consider the appropriate distribution for the container you're building, and of course, use multi-stage builds to only get what you need in the final package. So we actually have like 3 minutes according to my clock, which is nice. It's the first time I'm doing this talk, so I'm impressed with the timing, if anything. I hope you liked it. And so if you have any questions, we have about 3 minutes, or we can also do it in the discussion zone. I hope you enjoy the rest of .next. It's been fun as always, and I look forward to seeing you again. Thank you very much. I'm right, we have like 3 minutes, I think. Yeah. Yeah, cool. Questions. If you want to eat, that's perfectly fine. I will not be offended in any way. Yes.
Да, по поводу легкой миграции контейнеров. Сейчас есть такая проблема, как минимум с .NET, ну, с NetCore, что далеко не все Linux поддерживают NetCore. В случае с докером есть ли гарантия того, что очередной релиз очередной не самой популярной Linux-based системы будет его поддерживать, и нам не придется переписывать все свои приложения, все свои системы, которые написаны на докерах, уже без него? Спасибо.
Okay, but I mean, if you use Docker, then the host which is running your Docker engine, you can really use different distributions, and it doesn't matter what you use in the container image, right? So if you use Debian as the base image for Docker, .NET Core, and so on, you can run that Docker Debian .NET Core image on Fedora. That is fine and supported because Docker is supported on that platform. The base images Microsoft provides are basically just Debian, 2 flavors, and Alpine. So Microsoft doesn't actually give you lots of different Docker images to choose from, but you can run Docker on a bunch of different distributions, so you get the platform flexibility from there. Does that make sense? Cool.
So we are almost out of time.
Okay.